let's go ahead and get started with design tips and cost-saving tricks with the Gracia brothers. Today's presenters are Elijah and Riki Gracia. Elijah is a production engineer and process engineer at Royal Circuit Solutions in Hollister, California. He spends his days helping customers make boards better and make them cheaper. Riki Gracia is head of our sales team in our Santa Fe Springs facility. He spends his days solving problems for customers. These are two of Royal Circuit's best employees, in my opinion. I love these guys. So with that, can we take a quick minute for Elijah and Riki? Would you like to introduce yourselves?
Yeah, hey everybody. My name is Elijah Gracia, as you can see. And I've been working here on the engineering team at Royal Circuits North for the last 6 years. And hopefully I can add a little bit of value to your PCB knowledge today.
Hey guys, my name is Riki. As Mark said, thank you for joining us. I'm the sales manager here at our Santa Fe Springs location. I've been with the company for about 5 years, and I'm just here to help bring some insight on how we can help you get the most out of your design and still save on cost.
As we go through this presentation, I'd like to let you know that it is being recorded so you can view it later if the audio cuts out or anything on you. And also, as we go through this, there's going to be opportunities to ask questions. Oh, I guess I don't have that slide. But please ask questions in the question and answer box. We've got 2 employees here that are ready to, in addition to Elijah and Riki, that are ready to type out answers, or Riki and Elijah might field them live. It just depends on where it fits in the presentation and how we're doing on time. So ask questions as we go, interact, sit back, have a little lunch, have a little fun. All right, today's presentation, we're going to talk a little bit about background of board manufacture. We're going to go over VIAs, STACKUPS, and then finish with finishes. I know, that joke never gets old. All right, guys.
I'll give you a laugh, Mark.
I can't be stopped. I can't be stopped. Don't worry. It's going to get funnier the 3rd time I tell it in this presentation. All right. Elijah, help us out, man. Tell us, just give us kind of some basics of how boards are made and what drives up cost.
Yeah, definitely. So let's get right into it. So to start, here on the left side, we have an example of what one of our travelers might look like. And we just want to take a quick look at it in order to understand some of the cost-saving tips that we're going to be going over today. And so a traveler is basically the instruction manual, if you will, that we create for every order that comes through our shop. And once we figure out the exact approach we want to take to build your board, these are printed out and given to the production floor. And each traveler has its own custom instructions based on your design. These travelers can be anywhere from 2 pages to 20 pages long, depending on your technology. And so if you want to reduce the cost of your board, we want to prevent as many unnecessary steps as possible. So if we look to the right really quick, we have an image of an array. So this array has 64 individual boards on it. And the reason why we want to take a look at this is to explain yields, or the overall number of usable boards, and the level of risk that we take when we build your board. And as you can see, 6 of those boards have been crossed out. These boards might have failed due to overplating, maybe misregistration. Whatever the case is, we were able to yield 58 good PCBs out of the 64, or 91%, which is pretty good. So today we're going to be going over some tips that might help you improve your yields. This might be something that you've never considered before when you ordered your PCBs. Even though you ordered 20, we have to make more to prepare for overages and problems that we might face as we build your board. Anything to add on that, Riki?
Yeah, that's right. So when building a circuit board, it's, I mean, as everybody knows, it's custom manufacturing. So there are many different variables that go into manufacturing a quality circuit board that are often overlooked or just not considered. Working closely with both our internal engineers, some of our customers, and our designers, I've come across numerous instances where a small change at the recommendation of our team has not only saved money, but in my opinion, more importantly, time, right? So we're a quick turn shop. So time is very, very valuable to us. So the more steps or manual processes that we need to take while manufacturing your design, the higher your cost. So to combat that, Royal offers you several different tools and services, which we'll get into throughout the course of this webinar, But what I will always recommend to all of our customers is to take advantage of the services we offer and address any concerns about your design at the time of quote. Not only will this maximize the exposure our team has to your design, but it's going to help minimize any holds or delays to your order, any questions that our engineering team may have, which is, it's priceless. So yeah, we'll go over a lot of this stuff throughout the course of this webinar.
Hey, thanks, Ricky. Thanks, Elijah. All right. So one of the first things that I think we need to talk about from a design standpoint are vias. As a designer, I oftentimes want to use blind and buried vias, although I've never, ever been able to use one in my design. Would you tell us a little bit about how vias are formed, and then maybe explain why it's more expensive to use blind and buried vias, Elijah?
Yeah, definitely. So taking a look at this slide right here.
Oh, did you want that one up? Sorry.
Yeah, right there. Perfect. So a via is going to be a plated hole that makes connections through different layers. And on this slide, we see a few different types, like Mark was saying. We're just going to be covering, we'll be covering these in just a second, but first let me explain how the via is actually formed. And again, just so you better understand what we're going to be talking about today. All right, perfect. So Mark put together this great illustration. We start with a solid sheet of copper. The first thing we're going to do is drill a hole straight through the material. And so you can see there's that material in the center. The second thing we're going to do is add a layer of dry film around it. And what this does is exposes the copper that we're going to want to plate. So basically copper is going to be added on top, on bottom, and it's going to be barreled all the way through the hole.
Oh, sorry about that, Elijah.
No worries. Perfect. So the dry film goes on, and then we plate copper. Copper is being added to the top, the bottom, and a barrel down the center of the hole.
I'm failing at
You're good.
webinar running, Elijah.
Everyone's getting a good grasp of how a V is formed.
They're getting a good laugh is what they're getting.
Promotion
All right,
sickness.
so we do the dry film, and then we plate it up.
Yep. And then we're going to remove that dry film layer. And the reason why we do that is to be able to etch off the copper now. So that copper that's sitting really low, that's all going to be etched off. And what you're left with is a design that you asked for. So that's how a V is formed.
All right, so let's do that once again, start to finish without me interrupting. So just to be clear, so we start off with copper, and then we drill.
Yep.
We put on a dry layer laminate, and then I think we image that, don't we?
Correct. We burn
Okay.
off what we don't want.
Then we put it in etching tanks, which actually forms the via barrel and plating tanks, I'm sorry, and then builds up the copper. Then we clean the dry film off and throw it into the ferric chloride etching tanks, which then takes away a bunch of copper.
Perfect. Exactly.
All right. Thanks, man.
Fairly simple, and that image helps a lot. All right. So really quick, let's talk about some of those via names. That was just going over some of the simple one, or a simple via, but now we have these different types. So starting from the left, we have a buried via, or a plated hole that doesn't reach either side. And as the name suggests, it's buried into the board. Next to that, we have the blind via, which is a plated hole that starts from the top or the bottom, but doesn't reach the other side. The third image is going to be your standard via. That's what we just went over. And that's a plated hole that goes all the way through. And it's the simplest form of the via, or simplest form of making connections throughout the layers. So the next one is going to be the stacked vias. And these are made by drilling and plating your center layers, and then adding the next set of layers and drilling and plating again. And this happens over and over depending on how many layers you have. And that last example is going to be the staggered vias. Now, these are made the same way as the stacked vias. The only difference is that the design has the vias staggered or offset. See how they're kind of one's left, one's to the right. And it's really only used when you don't have a lot of room to work with in your design. It helps save a little bit of space.
Okay. So staggered, I think, are higher reliability than stacked. Is that correct?
Correct. Yes, because it's spreading out your ground plane. You're adding more connection.
So that's the way to go if space permits.
Yes, if space and cost permits, definitely staggered's great.
Okay, thanks, man. What about filling these vias?
Yeah, let's talk about filling. So there's a few different ways to do this. Let's start with the open via. That's just the standard via, no fill, no outside coverage. Everything's exposed down the barrel. So the first level of protecting that via would be to tent it. So here we're just going to cover them with solder mask, creating a blanket over the surface of the hole. And this is done when we are already applying solder mask to your board. So there's no added charge for this. Basically, this is on your design side. If you don't leave a solder mask relief, it gets tented, and that helps protect it. The second level of protection is going to be the LPI filled via. And here's where the hole is filled completely with the solder mask to give an additional level of protection from moisture and corrosion. And it's going to be your middle option. It's a little less complicated and cheaper than our last type, which is going to be the capped via, or also known as epoxy filled vias. And
All right, so
go ahead.
I was just going to say, so when would I use these?
So a good time to use an LPI filled via is when you're just trying to fill it without, there's going to be no connection basically, right?
Okay,
And-
so maybe I'm near a land pad and I don't want to have any solder wicking during the reflow process. So, and it's too big to tent, so I just fill it.
Correct.
Okay.
Yeah, so these are vias that aren't actually going to be used. They could be your thermal vias or whatever they are.
So
And
how big can you tent? I mean, what via diameter hole can you actually tent?
We can tent anything up to 50 mils.
All right. All right.
After that, it's just going to fall apart.
Yeah, or it becomes unreliable. All right.
Yeah.
I've got another question for you.
Mhm.
So when I create my design, right? Let's say I've got a 1/2 ounce copper board, and I'm going to plate 1 ounce copper on it, and I call out a 14 mil hole. Is the number that I give you the finished via size? Do you guys interpret that as the finished via size, or do you interpret that as the hole size, and the via diameter actually becomes smaller?
That's going to be your finish size. So if you're calling for a 14, depending on the finish that we're using, we're going to go up 4 to 5 mils bigger than that. We're going to drill a hole larger and allow for the plating tolerance to finish at your requested size.
Okay. And if I do something crazy, like I say I want it 14 mil plus or minus 1/10, that's going to cost more than I just say like 14 mil and just plus or minus 2 or 3, who cares, right?
Yeah, 3s are standard. If you go any tighter than that, it's going to cost a little more, but talk to us about that, and we'll see if it's even necessary at your time of quote.
Okay. I'd like to go back one slide for just a second. So we talked about these different things, and basically all the buried and blind vias start out as through-hole vias. It's just additional lamination cycles that either buries them or makes them blind. But what does it do to cost for all of these?
Well, so I think I can help on that, Mark. So one joke I've always had with my customers when they ask, when they introduce blind and buried vias into their design, they always ask, well, why does it cost so much? And my response is, well, do you really need the blind and buried vias? So for obvious reasons, for functionality purposes, they need to be there, right? Well, I've come to find that that's not always the case. So most recently, I had a customer who had a sequence of blind and buried vias to achieve a particular connection without shorting out the next layer, right? So the customer spoke with our engineering team. We were able to recommend an alternate method using a controlled depth drill. And that not only saved on time, saved on lamination processes, but it shaved days off of the overall turn time. So again, time is money. So it saved money, it saved time. So customer was winning in all areas of this build. Now, this isn't something that's always possible with every design, but it's an example of how options can be overlooked, or maybe engineers or designers just aren't aware of the different options that are available to them. So contacting our engineering team, getting quotes, getting everything processed with our team is going to help you save that. We're going to give you the best recommendations. That's going to make it easier for us to build, right? So the easier it is for us to build, the less expensive it is for you.
Thanks, Ricky. And you said controlled depth drilling, right?
Correct.
Okay, what's the difference between controlled depth and back drilling?
Elijah, I think, can help with that one, right?
Yeah, controlled depth is when you're only drilling to a certain depth. It's the drill machine's only going maybe, we'll say, half the thickness of your board. Back drilling is where we're actually going back and drilling a smaller sized hole through the already plated via. And what that does is it's guaranteeing your size or cleaning up the hole if it's something that's has a very tight tolerance.
So as a designer, I would use that on, say, a high-speed digital line where I'm worried about creating an impedance discontinuity. You know, you don't want just stubs of copper floating out there. It becomes just a source of noise. So, okay, so controlled drilling, I'm doing the drilling before I form the via, and then back drilling, I'm eliminating part of the barrel after. Is that correct?
Correct.
Okay. Thanks, guys. Let's keep rolling here. So we talked a little bit about via filling, and some of the reasons that you would use this from a designer standpoint. Really, it happens on the assembly side, right? If you have, say, a thermal pad with a bunch of vias going through connecting to your ground plane, those barrels are just going to suck all of the liquid solder metal right out of your, or you know, once it liquefies in the reflow process. It's just going to suck into those joints, and you're going to be out of luck when it comes to assembly. Your part isn't going to have enough solder to hold it down, or it's going to have poor thermal conductivity because now, you know, with the solder down in the hole, you're going to have air between your IC and your land pad. So that's no good. So we want to, the epoxy filled in cap's the best, but it's most expensive. LPI is less expensive, tinted is free, and open is free. So, right. All right. What about if I have some high speed and I need some, some impedance controlled traces? How would I go about talking to you guys about that?
Yeah, so as you might know, impedance is the combination of resistance, inductance, and capacitance. And to simplify that, here we're trying to control a specific circuit to flow at a specific current of electricity. And this is controlled by the trace width, the space width for differential pairs, and the dielectric spacing between the layers. Now this can be very time consuming for both you and the board shop. So hopefully you're taking advantage of one of our many impedance calculators out there, like the one on our website. And as an added bonus, we actually have STACKUP specialists on our side. Teresa and Omar are engineers that are dedicated to generating STACKUPs and including impedance modeling. So this is a huge tool and it can really help. So after looking at your design and your impedance requirements, we're able to create a STACKUP shown like this one on the next, right here, yeah, on this slide. And on the bottom, it's going to show you the impedance structures that you required. It's going to show you if we suggest any trace or space changes. We're going to use your numbers to calculate. And once it's calculated, if it's good, we're going to tell you it's good. If maybe we can adjust the trace size a little bit, we're going to let you know it's going to get you a better result. And on the far right, it's going to tell you that predicted current that we're going to get. So not only are we giving you the right trace and space that you should be using when you're modeling this, but on the top, we're also giving you the exact STACKUP that we're going to be using when we build your board. And from the engineering view, we love data packages that come completed like this. It usually means we're going to have clean data, little to no errors. The hard work's already been done, and it's a huge tool you guys should definitely be taking advantage of. So talk to your fabricator or your sales rep and start using this.
How much does that cost me, though?
It's free.
No.
We're crazy, right? You guys better take advantage of it before the owner catches on.
Yeah, so I just call Omar and Teresa and say, hey, I'm doing some work with the USB 3 line. I need 90 ohm differential pair and on a 4-layer STACKUP, and you guys just spit that out for me.
Yep. If you have your trace size, we'll punch it in and let you know if it works. If not, we can let you know which size you should be using, what the dielectric thickness. We give you all the details, everything you're going to need.
Nice.
Yeah. This is definitely a place or a spot where you can get the most bang for your buck, guys. Just like Mark and Elijah were saying, you know, we pay the engineering time, which is unheard of. So before we realize what we're doing, please utilize these resources. It's only going to help you out. It's going to help us out, again, when we're tooling the job and getting it prepared for manufacturing. Teresa and Omar, they do amazing work with making sure that your copper weights, your trace and space widths, impedance models, all of that stuff marries together, like Elijah said, in one clean data package. And that makes it very easy for tooling. It makes the process a lot faster. It ensures the build hits the production floor as quickly as possible. And that minimizes engineering questions, holds, any talk time, you know, that we have to call you to clarify notes, so on and so forth. So just like Elijah said, take advantage of this before we realize, you know, that this is something crazy we're doing here.
Absolutely. And sorry for the rapid slide changes. I'm working from home and I've got a cat who likes to type. So anyways, all right. So STACKUP. There's a lot of different times that as a designer, I use the word stack, you know, pad stack, different things. But when you guys use it, you're talking about basically the recipe for the board, right? All the different layers that are going to go together.
Yeah, we're going to talk about basically how we're building the sandwich that makes up your board.
Okay.
And so now that we've covered, oh, go ahead.
No, I was just saying, okay.
Okay.
I'm with you.
So yeah, now that we've covered vias and controlled impedance, let's go right into the STACKUPs. Here's another example of a STACKUP, or to put into simple terms, like we said, how we're going to build the sandwich that make up your board. And so every design is going to have its own STACKUP rules based on your overall board thickness, based on the copper weight you're going to be using. And when you add stuff like blind vias or controlled impedance, the rules start getting tighter and tighter. And obviously, the more layers you have, the higher the price can be. But there's a lot of misconceptions hidden in there also. And maybe Ricky can touch up on that.
Yeah, exactly. So one of the most common misconceptions we hear is, well, the thicker the board, the more expensive my board's going to be, right? Well, especially with rigid flex, that's not always true. It's actually the opposite. Once we fall under certain thicknesses, we not only have to change the machinery we use, but several automated processes now either need to be adjusted to accommodate those thinner dielectrics or have to be replaced altogether, right? So for instance, with flex material, standard mechanical drill is no longer possible. We have to use a laser drill just because the material's so thin. If we use, you know, our standard drill bits here, it's going to grab that like a piece of paper and just crumple it all up. And then, you know, we've scrapped your job and we need to start over. So thinner boards can be more expensive than the thicker boards. It all just depends on your design. Again, chemical cycle times need to be changed to accommodate the thinner material. Bake cycle times need to be changed, so on and so forth. So making sure we use the right STACKUP is crucial to saving costs and crucial to making sure that your board flows through our factory in production as smoothly as possible without any hiccups.
All right. So when I went up and visited the Hollister facility, I think that was, you know, a little over a year ago at this point, I saw this machine. What was this, Elijah?
Yeah, that's going to be our lamination machine. That's how we're pressing together all the layers that are going to make your final board.
So how do you control the thickness of the board? Is it just you squeeze it together and whatever happens, happens?
Yes, of course. No. What we actually do is so basically you have cores. Cores are a piece of material with two sides of copper. Perfect. So that green one is going to be a core, right? That green little layer. So it's 10 mils thick right there. And then it's got 2 sheets of 1/2 ounce copper on the top and the bottom. And what we're going to do to create more thickness of your final board is we're going to be adding sheets of pre-preg in between those little yellow slivers right there. And we can add different amounts, different types at different thicknesses to achieve whatever thickness you're trying to get.
Okay, so if I want a board that's, say, 62 mils thick, I just tell you I need something, a 2-layer board that's 62 mils thick, or do I need to go out and figure out what all to choose?
To save the most money, just let us know that it's 062 and let us do everything our way. That way we're going to use the common materials that we have, and that's saving you money. If you start asking for specifics, it might be something we don't have in stock. It might be something that we have to special order. Those usually cost more money and also come with a lead time. I think we ordered a special material for a customer yesterday, and it has a 28-day lead time. So they have to wait 28 days for the material to get here before they even start the job.
Was that like a nylon
Yeah.
for RF? Yeah, that happens. Okay. We've got a question. It says, how do you define rather layers as 0.5, 1 ounce, or more than that? So I think the question is, how do you define how much copper goes on a layer? How do you tell somebody that?
Yeah, you can either tell, I mean, the most simplest way to put it is you can put 1/2 ounce or 1 ounce or 2 ounce, literally writing it that simple on the board. Or what you can do is, if you're not sure how everything works, just give us what you want the final thickness to be. I think 1/2 ounce is usually 0.6 mils, or 1 ounce is gonna be 1.2. And you can tell us, hey, that's the finished thickness I want, because inner layers are gonna start and end at the same thickness. But outer layers, if you remember how we're building those vias, they're gonna get plated up on the outsides. So even though we're starting at 1/2 ounce, it's gonna finish 1 mil thicker. So it's gonna be finishing about 1.5 mils.
So when I define my via plating, let's say I want 1 ounce plating for my vias, that 1 ounce is also going to be added to my outer layer, right?
Correct.
And if for some reason I wanted 1/2 ounce and not 1 ounce, is there anything to do about that?
Our standard is gonna be 0.7 mils in the barrel.
Okay. So whatever I ask for in my barrel, that's what I'm getting on my surface as well.
Yeah, by standard, it's always going to be 0.7 mils. If you want anything more than that, it's going to have to be in your fab print or README notes. And it's as simple as letting us know what thickness you want inside.
Okay. Is there any way to plate those vias completely shut?
To an extent, yes. This is where it gets a little tricky. Up to a 20 mil board, it's fairly simple. Once you get thicker than that, we'll basically have to build it in multiple sandwiches and try to connect multiple plated drills together, which is a little tricky, but we do it.
Okay. Well, hey, can you briefly tell me about balanced versus unbalanced stack-ups?
Yeah, definitely. So if you look on the left, everything's very symmetrical. If I were to cut that straight down the middle horizontally, the top half is going to mirror the bottom half. If you look on the left, if you look on the right, you can see there's a lot more pre-preg on that bottom. It looks like there's 5 sheets on the bottom versus the 2 that are on the top. So it's a little uneven. And what that's going to do is that bottom side is going to be it's going to hold on stronger than the top side. And whatever that bottom side wants to do, if it wants to bend or bow, the top side is going to follow that. So what you're going to end up with is a potato chip instead of a flat circuit board.
So why do people do this, do you think? Why do people design unbalanced stack-ups?
I'm not too sure why they do it. Usually it's, I guess, from my side on engineering, it's going to be they're looking at their controlled impedance or trying to get a specific size via going through there. And they're really only focusing on the one side, not paying attention to the other.
Yeah. So one of the things I often see on the assembly side is people will start off with a balanced stack-up like the one on the left, but then they remove so much copper and in very particular patterns that they unintentionally create an unbalanced stack-up from something that was stacked up before, right? It's not so much a problem when you've got copper pores all over the place, but if you've got, just for example, a 2-layer board, and on the top layer, all the traces are running horizontally, and on the bottom layer, they're all running vertically. Well, it's unbalanced again because you've got stresses in perpendicular directions, and you end up with that hyperbolic parabola. So anyways, interesting stuff.
Yeah, and that also applies for copper weight, not just the pre-preg. If you have a 3-ounce copper on top and then a 1/2 ounce on the bottom, it's going to do the same thing.
Yeah, from the varying coefficients of thermal expansion. So interesting. Thanks, man. All right, now my favorite subject of the webinar. Are you guys excited?
Of course,
Excited.
always. I already know what it is.
I know, because we did a run through. So I mean, yeah. So anyways, all right. For any of you heavy copper people out there, a lot of the online calculators are referencing IPC 2221, which is now deprecated when it comes to high current heavy copper traces. It's been replaced by IPC 2152. The reason that you've never run into trouble before is that IPC 2221 is way overly conservative. Basically, you're using too much copper, more copper than you need to. So you might be able to save a buck if you change from 2221, which is old and busted, and you move to 2152, which is the new hotness. Doctors Douglas Brooks and Johannes Adams took all the data from 2152, which was empirically derived, by the way, and they came up with equations for it. So what you're looking at right now is from their work. We're looking at sea level at standard atmospheric pressure, the amount of copper that you can run through various, the amount of current that you can run through various trace widths and various thicknesses to only see a 10 degrees Celsius increase in your board temp, okay? So reasons you need to worry about board temp increases. One, I mean, if your thing's installed in an automobile, say, you know, at 80 degrees Celsius, and your fiberglass transition temperature is like at 100, well, if you have a 20-degree rise, then your board's gonna melt. It's gonna, you know, release all the magic smoke, your design's gonna fail. So you have to look at the glass transition temperature and stay well below that. You have to look at how do your components derate, you know, the nearby components. Do you have a temperature sensor running near this high current trace? I mean, I would hope not, but what about your capacitors? They derate with temp. So there's a lot of different reasons that you would not want your temperature to go too high. Anyways, in our blog, you will see that we created a bunch of these charts based on their data. And as an example, let's say you know that you can have 2 amps of current continuously running through a trace. How much copper do you need? Well, if you're dealing with ½ ounce copper, you need something like 90 mil trace width. If you're dealing with 1 ounce copper, well, okay, all of a sudden now you can get away with a 50 mil. And if you are dealing with 4 ounce copper, well, you only really need 20 mil. So we have these charts that give you estimates, and they're estimates only. The final responsibility is yours, but they're based on the works of Douglas Brooks and Johannes Adams. And we've got them for a variety of temperatures, everything from 1 degree up to, I want to say we made them up to like 70 degrees Celsius. I'm not entirely sure. But if you need help getting those, we can get them for you. All right. We've got some questions for you guys, but I'm going to pause those until the end. Also, and we're going to update this in the very near future, tell me about trace and space minimums.
Yeah, definitely. So trace and space minimums, that's another factor you want to take in when you're talking about copper weights. And so in this slide, we have a chart of the trace and space minimums. And so on the bottom left, we see a chart version, and on the right is the graph version. This is something we're going to use here at Royal every single day. I have it pinned to my wall. I check it for every single job that comes through to make sure that I'm releasing everything properly on my side and making sure that the customer has followed the rules that we're giving. So a quick example, if you take a look at that top line, if you're using 1/4 ounce copper, 0.25 ounces, the smallest trace we can get is 3 mils. And the smallest space we're going to be getting on an outer layer is 3.5 mils and 3 mil spacing on the inner layers. So on this chart, each copper weight shows the different trace and space minimums you're allowed. And that's to make sure we get a good yield rate and keep your costs down. And we get asked a lot if we can break these tolerances. And in short, yes, we can absolutely break these tolerances. These are our advertised minimums. To break these rules comes with obviously a cost adder because it's going to take us more time, more materials. We're going to have to build extra to make sure we're making up for the overage that we're going to lose. And yeah, basically, that's pretty obvious, right?
Yeah, so you can, it's just going to decrease your yield, which then increases the cost.
Correct.
Okay. All right. Rigid flex is a whole other beast when it comes to design. There's some new rules and some other things. Do you want to tell me a little bit about the you know, some things I might not know about rigid flex design, Ricky?
Yeah, so when it comes to rigid flex or flex in general, your layer stack up isn't just always copper and dielectric, okay? Adhesives and stiffeners also come into play. So I know I sound repetitive, but I can't express enough how important it is to take advantage of our resources. Our engineering team can recommend the best options for your design. Every flex or rigid flex design that I've seen is custom, with it being, as I would say, newish to this industry as it is. Everything needs to be touched. I recommend, anyways, it be touched by at least one of our engineers so they can help you along the process. But for instance, you may not need a 4-layer rigid flex, right? So you may have designed a 4-layer rigid flex for your application, but when it gets to our engineers, they may be able to modify your design, obviously with your approval, and turn that 4-layer rigid flex into a 4-layer flex with stiffeners. And the reason why I use that example is a 4-layer rigid flex is going to be less cost effective than a 4-layer flex with stiffeners, right? So we're not using as much material for one. We're decreasing the amount of lamination cycles that it has to go through. A lot of the processes get changed and are made a lot easier. So that's where the price is going to derive from. But if we can add those stiffeners in crucial areas, that's going to help with your costs. So just to briefly cover stiffeners, it's just a piece of material, whether it's FR4, stainless steel stiffener, capped on polyimide. There's several different choices, but it's generally placed in a specific location underneath the area where your component is going to be placed at time of assembly, right? And what that stiffener does is it provides rigidity while allowing the other portions of the flex to bend and move. That's the general purpose of a stiffener. But adhesives are not only used to fuse, bond ply or cover lay, but it's also used to adhere the stiffener to the flex circuit, right? So, and the reason why I bring that up is the adhesive itself is also going to increase your thickness, right? It's going to add space in your stack up. So at times, options may be limited based on how the flex needs to bend or the rigid flex needs to bend. In this case, the thicker the board is, the more your bend radius will be reduced or affected, and vice versa, right? The thinner it is, the more pliable it will be. And again, that's going to change, dependent on the material that you're using. Those have their own bend radiuses and so on and so forth. So each design will be its own individual case. So again, talk to your account manager, your sales rep, talk to our engineers. We're going to recommend the best material for your application, and that's most cost effective and readily available. Again, that's going to save you time in us obtaining material if we don't stock it, and it's also going to save you on cost. If we have it here in-house, we have a lot more room to wiggle with things of that nature. So make sure that you talk to us and we'll get you what you need.
Hey, thanks, Ricky. All right. Oftentimes we get questions about pre-approved STACKUPs, right? Do we have a standard STACKUP that designers can use? Do we?
So in short, yes. Elijah, do you want to touch on the pre-approved STACKUPs? Elijah?
I think we've lost Elijah. All right.
Hello.
So,
I'm
there
here.
we go.
I was muted. I was talking, and you guys were asking for me.
Sorry.
Okay.
So tell us about the pre-approved STACKUPs, buddy.
Yeah, so in short, there's two things you can follow for pre-approved STACKUPs. First, take advantage of our STACKUP calculator and our STACKUP engineers, like we were talking about. They're already going to use the things that we use the most, that we have in stock, right? And these two free tools are going to help figure out some of your design rules and give a STACKUP built by us and approved by you and help you get everything running smoothly. So basically, we have a stock room, right? And there's over $1 million worth of material in that stock room. We carry everything that we can possibly afford to carry, right? because certain things have a shelf life, and we don't want to carry something that we don't use too often. So in short, like we were saying earlier, you want to ask for the thickness of your board, your final, like say an 062 board. Let us know that you want an 062 finish if you don't have any specifics, or just let us know the thickness. Like if you see on the thickness side to your left, between layer 1 and 2, you have 7.9 mils. Just let us know you need about 8 mils in between there, 39 mils in the next one, right? Let us know those thicknesses, and we're going to use common materials that we already have. And because like we said, if you start using your own stuff, it might be something we don't have. The first step is we're going to put it on hold and suggest that you use something else. And if you absolutely have to have that other material, then we're going to have to go and order it. And it just prolongs the process, adds cost. And that's not what we want to do today, right?
Absolutely. And something I'll add just from a designer's perspective, look at the difference between the separation in layers 1 and 2 and 2 and 3. 1 and 2 are separated by about 8 mils, and 2 and 3 are separated by about 40. Now, a lot of designers use an old STACKUP where, you know, you have signal, power, ground, signal. But the trouble with that is when looking at your return paths, there's not a whole lot of coupling between layers 1 and 3. You know, you're looking at 48 mils distance, versus if you routed your return paths on layer 2, then you've got a, what is that, a factor of like 25 better coupling. Take a listen to Rick Hartley if you ever get a chance, and he'll talk to you about some better STACKUP or some better routing you can do with your typical 4-layer or 6-layer STACKUPs. It's not the old school isn't the best. So anyways, with that, let's, I know you guys were waiting for this, finish with finishes. Don't worry, folks, I'll be here all week. All right, so we put finishes on the board to protect them from, you know, mostly to get them through to the assembly side, right?
Correct. So there are many different options when it comes to finishes. We want to make sure that you pick the right finish for your design. For those who may not know, like Mark started to touch on, a finish is used to protect the copper, right? So copper oxidizes quickly when it's exposed to oxygen. Oxidized copper will not form intermetallic bonds. So finishes are used to combat that oxidation and make sure that your board stays reliable. So we'll go over some of the most common finishes here, and we'll start off with hot air solder level, or hassle. This is achieved by covering the exposed copper surfaces of your circuit board with a molten solder. It's the most economical option cost-wise, but it's also the least consistent, right? It varies in surface height, which makes it difficult for paste stencils during assembly and makes a paste printer application unavailable. It's completely obsolete. We can't do it. This will save on cost on your board, but it's going to add costs during assembly, right? So assembly is going to have to use different processes and increase the cost on that side. So that's the plus and minus side of hassle finish.
Let me make, I think you misspoke there for a second. You said the paste printer was obsolete, but like jet paste printer is actually the way to go. I think you were saying the stencil printer is obsolete.
Sorry, yes, stencil.
No worries.
Sorry.
No worries.
Got it. So, and our next finish that we'll go to, secondly here, we will have organic solderability preservative, or an OSP finish. OSP is achieved by applying a thin layer of chemicals to the PCB, and this is shielding the copper from oxidation. It's also cost effective, and unlike hassle, it lays flat, making assembly paste options easy. The downside is that it's fragile, right? So almost like a really thin clear coat on your vehicle, it's vulnerable to scuffs and scratches and chips, and it may expose the copper and compromise your board integrity.
How long, do we know how long these boards can sit before assembly with these two finishes?
I do not.
It's going to be about 6 months.
Okay, thanks. And then we also offer ENIG and INIPIG, right?
Yes. So ENIG, or electroless nickel immersion gold, is when nickel is deposited over copper in a catalytic reaction. Once nickel has adhered to the copper, it's plated with gold to assist the conductivity, right? So this does carry a minor cost adder that you can work with your sales reps on, but it has proven to be one of the most effective finishes offered. It's durable, lace flat, and very common in our industry so far. And then NEPIG, or electroless nickel, electroless palladium immersion gold, is similar to the ENIG, very durable, very similar process, but it includes palladium, and the palladium is deposited after nickel and before the gold, right? It offers, like I said, the same durability as ENIG, with the added feature of being wire bondable. So for your wire bondable designs, this is definitely a finish to consider. But again, all of these are some of our just more used finishes here at Royal, or both North and South. But choosing the right finish for your design and application is critical. So there are more finishes offered with different flavors, such as hassle lead free and so on and so forth. And these are just going to be our most common and cost effective ones currently.
All right. Can you, just off the top of your head, tell us a little bit about things that affect turn time and cost? Are there any decisions that you've seen customers make, or anything you've been able to help them not do that's really improved the experience for them? And this question's for both of you.
So on my side, a lot of things that I see is customers. One thing that we did touch on was the non-conductive via fill. That's definitely one thing that can save you on time and money. Non-conductive via fill, we can turn that on a rigid build. I believe our northern facility can do that in about 3 days, but it's going to cost a lot, right? So that process spins that board through the shop about 1.5 times. So that's one of the key things that you can definitely save cost on. Again, if you can do LPI fill or something like that, if it's a prototype board, that's something that will definitely help. Picking the right material is another one that I see here in my shop almost daily. Like Elijah said, there was a material that needed to be ordered that had a 28-day lead time. Currently at our Flex division, we have a material, our AP material, that has anywhere from an 8 to an 18-week lead time. So it can get out there sometimes. So choosing the right material, if you're able to substitute material or let our engineers recommend an alternate material, an equivalent material, that's probably some of the best deals that we have to offer in saving you time and money.
Okay. And then Elijah, I know you've had some experience helping customers out. Are there any decisions that you've seen that you don't recommend? Or?
Well, I think the first one would be find a different hobby. That's definitely going to save you the most money right off the bat. But if you can't do that, then, well, we have a few different options like we covered. Using those pre-approved STACKUPs, using the pre-approved materials, getting clean data from the very start. We have so many tools and resources that we're giving away for free every single day for every single order. Definitely take advantage of those. Even if you don't know what your STACKUP's going to be, give us a shout out, shoot us an email, and get in touch with our STACKUP engineers. They are dedicated to doing STACKUPs all day long. And that's going to just start us off properly. If you get a chance, go and check out our DFM and DRC webinar that we did. Just go ahead and give it a replay. And those are going to be the design rules to start you off from the very beginning with success.
All right. Thanks, guys. With that, we've got a few questions that I've been holding for us. So maybe we'll just start at the top and work our way down.
Sounds good.
So Ray asks, what's the typical etch factor for half-ounce copper on inner and outer layers? So maybe the etch compensation he's looking for?
Yeah, so I'm sorry, was that 1 ounce or half ounce?
Half ounce.
Half ounce, we're going to bump it up 1 mil, and that's going to be done on our side. So as long as you follow our minimum trace and space rules, we're going to add the etch factor on our side and etch accordingly.
So for those of you wondering what we're talking about, when you etch copper, it doesn't etch straight down. It doesn't stay perpendicular to the board. It's like a trapezoid. So to make sure that the trace is big enough at the bottom, we have to increase the size of the trace at the top. That's the etch compensation or etch factor that Ray was referring to. Thanks, Elijah. So question is there a preference, or why would you use foil and core construction versus all core construction? So see, like a 4-layer board, we start out with 1 2-layer core, and then we add layers on either side, or do we take 2 2-layer cores and glue them together?
Yeah, so the preference is going to be a foil construction, which is foil on the top and the bottom, and then the center is all cores. And the reason for that is when we're building the insides first, we're able to do 2 layers at a time. It makes it so simple. There's less registration problems that we're going to have later on down the road. Plating is easier. So when we're making your final sandwich, we're able to finish off with just a single sheet of copper on the top, and all your inners are already completed. It just makes everything so much easier on our side.
Interesting. I would have thought that the 2 cores would have been better because you could, but no. Huh. Okay,
Yeah, we get,
good to know. I'm glad you asked that.
Yeah, you get some moving going on, so misregistration can happen, and we also add more processes to get those outer layers imaged.
All right. Well, thanks for asking that, Tim. I had a misconception that you just fulfilled there. Okay, let's see. Alani asks, are there any concerns with lack of copper trace uniformity across a larger board? For example, if I have a few small traces running in one small area across the length of the board and no other copper around the rest of the board on a particular layer, are there manufacturability concerns? So I'll let you guys get into slivers and all that in just a second, but to answer your question, Alani, the dielectric expands much more than copper does. So if you have, let's just pretend you have a 1-layer board for just a second, and on the top you've got a bunch of parallel copper traces. Well, in that area of the board, there's nothing constraining the expansion in the perpendicular direction, perpendicular to those traces. So the copper holds it together in one direction, but it's not holding it together in the other. So that would cause it to curl, to basically roll up. Now, is it rolling up like a burrito? No, it's not rolling up that much, but it might be enough that when it comes to assembly, that your board's not flat enough to stick those parts on anymore. So try to keep the copper on both sides of the board as even as possible to prevent that from happening. Because if the stresses are equal on either side of the board, your board's going to stay flat. I don't know if that makes sense. All right, now for slivers and all that. Elijah?
Yeah, I'm sorry, what was the question regarding slivers?
Any concerns running copper traces across a large board? So if we have, let's say 4 parallel copper traces running across 12 inches, I don't know, something long.
Yeah, I mean, it's basically what you said. We are going to get that chance of warpage because, like you said, one side's going to be stronger than the other, and it's just going to want to give. So yeah, it's not only STACKUPS, it's also design. You always want it to be uniform.
Okay. What do the vias should be 100% plugged or preferably left open when using IMAG? Immersion silver.
Oh, silver. Okay. So, yeah, it's basically on your design. It doesn't affect the board, or I mean, I guess it doesn't affect the process on our side.
Should we plug the vias or leave them open?
It goes either way, whatever you prefer. It's not going to affect, at least on our side. I don't know about the assembly side, but production, it's no difference.
All right. Anonymous asks, to fabricate to IPC 6012 class 3, what size annular ring would you require on plated through holes?
5 mils annular ring is what we require.
Okay. And then Murat, I don't really understand your question. Maybe you guys do, but he says, don't you do thieving? We
do not do thieving on our side. Some board shops do add thieving. I guess that would kind of go with the slivers, right? We don't add any thieving on the board. If you have a few traces on one side and nothing else, some companies will go in and add little thieving dots onto those layers to help fill the gaps and make everything uniform, but we don't do that at Royal.
Okay. Well, with that, I would like to thank everybody for joining us. We do have one more. I don't know if we're equipped to answer this, but it says, does tinting of vias cause long-term reliability issues with trapped chemicals in the holes or anything?
Yeah, definitely. Depending on, what's getting stuck in there, it can cause long-term issues. That's really more for maybe prototype boards. If it's something that you plan on using long-term, you should definitely be either plugging it all the way or, again, the epoxy via fill, which is also copper plating over both top and bottom.
Yeah, but prototypes, I mean, they've got a life of 6 months or something, so it's not going to happen in that time frame.
Yeah.
Okay.
Exactly.
All right. Okay. So this one I think I can answer. You guys can correct me if I'm wrong. It says, for a design that requires filled vias, do you recommend filling all vias or only the vias that require filling? If you're paying for the process, I mean, just do them all, right?
Correct. Cost the same if you do 1 or 100.
All
Exactly.
Right. Okay, now we are out of time, so I'm going to end this. But if you have any questions, please contact Elijah at royalcircuits.com or Riki at royalflexcircuits.com, or call our main number 831-636-7789, and you can reach them there. Next week, we've got the very exciting Chris Hungrath of Inselectro, who's going to tell us all about rigid flex and flex design. Chris is a walking encyclopedia, and I mean that literally. The man is a genius. So if you have a chance, join us these next 2 Thursdays. It's going to be a 2-parter. Also, Royal Flex and Royal Circuits was recently featured on the brand new Moore's Law podcast. So if you have a chance, check that out wherever you get your podcasts. We thank you for joining us today, and we hope you have a great rest of your day. Stay safe, and we hope to see you soon. All right. Thanks so much. Take care, everyone. Bye.